Hey, so I was kind of on a roll yesterday doing these Python tools, and I made another one. You can see on my channel the previous video, which was about this export quick materials node, which just yeah, well, I just thought you can watch that video, but it's basically for how you can take a model with a quick materials type setup or OBJ importer type setup and export those materials with the texture assignments via the ROP FBX. Anyway, that's not what this video is about. This video is about another optimization, not really an optimization, but an important thing to make this model workable in the game engine, which is to combine those multiple materials into one material. And it's sort of actually, interestingly enough, what that quick materials setup was doing in Houdini, because it has one shader and then it uses material overrides to apply the textures to the different areas. Now, obviously, there are ways to kind of simulate that in the game engine. For example, you could use vertex color and switch between the different textures there in your game engine shader. But that requires a custom shader in the game engine, and it'd be much easier if you could just use a regular shader. Just get the UVs, apply a texture, and call that a day. So in order to do that, what you basically have to do is take. So this thing currently has like different groups of primitives which have different materials on them. As you see, there's all these different material names on the different primitives here. And what we need to do is combine all these materials, all these textures into one texture. It's called an atlas, or similar to like a sprite sheet, I guess. And then manipulate our UVs to look up the textures at the correct positions. And kind of long or the short of it, okay, and the benefit of that is, instead of importing this into your game engine with many materials, you're going to have one material, which makes it much easier if you want to write a weird shader for it. You don't have like 5 shaders now for the single model, for example. So I'll just show an example. If I don't do this, you can see what happens. I just have this export quick materials like I showed yesterday. I'm going to save to disk. Load this into Unity. I extract the textures here. And as you can see, there are 5 different material slots on this. Okay, in order for this to show up, because it's Houdini units, you have to scale it by 100 right here. But yeah, so you can see this does work correctly. There are 5 different materials, so it makes it a little tricky to write custom graphics logic for this thing. And let me just kind of show the result of my new tool, and then I'll dig into a little bit about how it works. So the combined textures node here, I'll get into these parameters, but let's just say for now I just press execute on that. It's going to take a little while because there's a compositing step in there. It's loading a bunch of images. These nodes are non-procedural, so I do have to press execute on them whenever I want them to run. And then this ROP FBX, I can export that as well. And now in Unity again, it's importing this thing. And these textures aren't being used right now, so let me just demonstrate this. So this one I can, again, extract the textures here. And you see it looks the same, but the actual texture is as you see, it's all 5 of those textures packed into a single one. So what the tool actually does is it automates the texture process. So let me dig into this a little bit. So what the tool does, it first of all kind of detects all the materials on the model, and it expects that sort of quick material type setup with the material overrides, and it looks through the data there, and it finds all the different texture paths. It automatically creates a cop net where it imports all of those different textures here into a sequence and then into a mosaic. I don't know why there's two of these, but whatever. Yeah, and then this mosaic here is the output image. And then what we basically do is we calculate UV offsets for each of those materials. So, for example, since this image is in the lower left quadrant, we basically, for all the primitives that have this particular material assignment, we calculate the bound. So the x bounds is going to be from 0 to 0.33, and the y bounds is going to be from 0 to 0.5. And so we take the UVs and we remap these ones into that range. These ones will be remapped into a different range. These ones will be remapped into a third range, etc. Everything, all UVs will get remapped into the range corresponding to the position of their texture in this atlas. And that is done automatically. To get into the specifics of the technical stuff of this, there's a bunch of Python here, which creates this CopNet, and it seeds data into this outer wrangle right here, such as it detects the basically grid layout. So let me actually just get into the parameters here before I kind of dive into the internals. So you have three parameters. There's the output image path, the cell resolution. So originally these images were actually 4K textures, and so I don't want to pack 6 4K textures into one because it's going to be enormous. So what I do is I just lower each of them to 512 by 512 pixels, and that keeps this overall resolution low. And cells per row is 3. So that'll just make in this case, there's 5, so it'll make a 3 by 2. And it goes from the bottom to the top, left to right. So it's like 1, 2, 3, 4, 5. And yeah, so that's pretty much it. Then you just press execute, and it'll rebuild all that. So I can kind of, if you want to, oopsie. So it's let's try with a cells per row 2 layout, and you can see how it's a little different. Yeah, so if we go into this CopNet here, CopNets are a little slow because it's a lot of memory in there with the loading the textures up. Okay, there we go. Yeah, so here's our mosaic. You can see it's 1, 2, 3, 4, 5. It's using the 2 layout. Anyway, so we kind of calculate the these right here, this data. Well, it's I kind of don't know if I should get into the internals of do a full walkthrough of how this works. But let's just say that it might be a little TMI because it's a lot. It's kind of a lot. So I'll just dive into this. You know what? I'll just kind of I'll just walk through the whole thing, whatever. So, but if you don't really care that much about how it works, you can go on Orbolt and download this combined textures thing. And yeah, so, but let me dive into this fully how I create some of these Python tools, which I haven't really done in some of the other previous tutorials, but I'll just explain that one here. So basically you make your HDA, you make a subnet, geo level in this case, and then I convert it to a digital asset. You make a subnetwork, right click, digital asset, create, and then that'll open up, you open up the, the type properties. You probably already know how to do this. And then basically what you want to do is you need to make a Python callback. So in this case, I just have this execute button here. So if I basically drag in this button parameter here, and then if I go into the button, if I click on the button and I look at this callback script, you have to you do the Houdini who.phm, which is Python Houdini module, and then in your Python module, you can define any function, and you just call that here, and then you pass in this special thing called keyword arguments or kwargs. Okay, this is sort of just boilerplate in order to run your function. In the execute, this can be named anything. I just named my function execute. And then if you go into the scripts tab here, what you basically do is, let me just show you. So you have an empty one, Let's just create a digital asset here. That's fine. And then if you go into scripts right here, you go to this event handler and you click on Python module, it'll create one for you, right? And then, you just do your def execute quargs, and then in here, you can do whatever you want. That's basically how this Python works. Okay. And so now if we look into the actual specifics of my tool, right, of what this Python does. So right here, you get the node from the keyword arguments. That node is this node, so that's a handle on this node. And then I get a handle on the geometry, which is important here because I need to read some primitive attributes. Oh, I'm sorry. So in this case, I'm not actually reading this node's geometry. I actually did that originally, but it was buggy. And the reason that doesn't work is because when you read the geometry of this node, it's actually reading the output geometry. So the first time I ran this script, reading the geometry of the combined textures node, it worked because I hadn't changed the geometry. But then when I ran it a second time, it was reading the output, and the output was different, so it didn't work. So what I need to do is add like an input null here inside of it and use that as the source of my geometry. So that's what I'm doing here. The output path, so here I'm just like reading some parameters from the combined textures node. I'm reading this output image path, cell resolution, cells per row, just into variables here. What I'm doing in here is I'm checking, so inside here I basically want to delete the copnet if it already exists, and then create a new one. So I say the old copnet, and then I look for the copnet, and then if it exists I destroy it, and then I ensure that there's a new one. Here I'm creating a dictionary of that material data. So this is where I'm looking through the geometry of that input. So I say for primitive in all the primitives, I find the material name attribute, which as we looked in the spreadsheet was the unique name that identified which material was associated with the primitive. And then I load the material override data. And in this material override data is the base, is the texture. And so you do have to JSON parse this material override. This is actually a string that's serialized to JSON. So use this JSON loads method. And I then get the base texture. So I'm basically mapping the material name to the texture here. That's what this whole little block is doing. And then, so basically, then I just do some stuff to fill out this copnet procedurally. So I create a sequence node in here, starters, and then I iterate through all of the material names. I create a file for each of them. I set the parameter, the file name 1 parameter. So in order to see the parameter names of everything, obviously you can just hover over this. You can see parameters, file name 1, file name 2. Let me just make sure I'm recording this. All right. And then, and then you just do the file node param this, and then you set it to the value you want. And then if you need to connect them all to the sequence. So I just do sequence set input. Like I want to set the 0th input here, the first input here, the second input here, third input here, etc. So then I need to set some parameters on the sequence. I want to set the scale to new size. And then I want to change this resolution match to specify resolution. And then I want to fill in these size ones. And this is how I'm resizing each of the images. And then I create the mosaic node, do some settings here to lay it out correctly. So I want this images per line that sets up how many there are per line, obviously. I set the input. This T range, that's what it's right here. I'm just saying I want to stack them. The first one's at the bottom because by default the first one will be at the top, and then you're gonna have to like reverse your UVs, and it's annoying. So anyway, and then I create this raw comp output. I set the output picture path from the parameter that we've set, and we just use press button here to do a render. And whenever you're creating nodes procedurally with Python, you always want to do this layout children thing. That'll just make everything look nice. because otherwise everything will be stacked on top of each other, very ugly. Okay, now we have our texture created. Now we need to do the UV manipulation. So basically I get a handle on my node set data here. And what this is going to do is it's going to just save some data to the primitives, which I can then... So the rest of this whole chain is mostly unaltered by the script. So, but this set data is sort of has some parameters here that I am changing from the Python. So yeah. What is this doing here? So it's finding the num rows, just using a bit math. I'm taking the number of materials divided by the cells per row. So, for example, if I have 5 materials and cells per row is 2, that's, you take 5 over 2. I think it's like 2, and then you seal that. So that's like 3. So that's saying I want 3 rows. That's how you calculate the number of rows here. And yeah, and so then I'm then setting this is the number of the number of columns, and then this is the number of rows. And sorry, so yeah, did I feel like now that I'm looking at this, I think something got messed up here. I don't know why this stuff was here twice. Okay, that was an issue. That's why those things were being duplicated. Okay, I don't know what happened with there. Must have accidentally copied that. Anyway, that's why I do these videos. No, I'm just kidding. Also, I have this stuff twice. What? Okay. Did I have this stuff 3 times? Anyway. Okay. So we've set that. Now we also need to set this data stuff here. So this is like basically saying which cell each material name is associated with. So how do I do that? I go for material name and material data. Yeah, it's just a little bit of math. You take the... So say for example, this one is index 0, this is index 1, 2, 3, and 4. Right? So index 0, you do... Or say index 1, for example, right here. So you take 1, which is I, divided by cells per row. So that's divided by 2. So, and then you floor that. Right, so that's saying that this is now going to be on the 0th row. So, so if you take number 2 and you do like 2 divided by cells per row, that's 1, right? And then this 3 divided by 2, that's going to be like 1.5. But then you floor that, so then that's how you get it's on row 2 in the middle, etc. So that's how you get the row index, and then the x here is just the modulo, basically. So 1 modulo 2 is going to be 1. Yeah, I don't know. Okay, just a little math shit, whatever. And then we just put that into JSON format. I'm storing these things. I would love to store these as vector 2s, but it just seems too difficult. So I'm just storing them as strings, comma-separated strings. This is JSON serialized here. Essentially, I build up this dictionary, I serialize it to JSON, and I dump it in this little data thing here. And then that's pretty much it for this Python. I know that was a mouthful. And then in here, I mean, okay, I think this just does remaps basically. So it does. I don't really want to explain this, but this just like takes this data in here and figures out the different ranges where we need to remap the UVs. So for example, like this is going to be in cell 1, 0. Okay, so so we take that data and then we split it into that vector 2, like I said. This is the 1, 0 coordinate here, and then the I don't think I needed that. Okay, and then And then yeah. Oh no. And then what do I do here? Actually, so this isn't actually manipulating the UVs. This is sort of pre-computing that data. So I'm calculating the range for the UVX and the UVY. Yeah, and it just like I don't know. Yeah, this is math and it works. You can look at that if you really want. Okay, so and then I attribute promote this like range attribute from the primitive to the vertex. Vertex is where the UVs live. I do the same to the Y. And then here in this vertex wrangle, it's very simple. I just literally apply that remap here on the UVs. And now in this quick material, I apply the new texture. And, you know, if you, it's kind of interesting, if, let's see here. Is this pinned? Let me see something right here. Right, so, so if I go in here, yeah, this is what I was trying to show. So it's like I'm doing this vertex, this UV manipulation right here, and it gets all messed up. But then when I apply the Atlas texture, then suddenly it looks correct. So anyway, that was a shitload of talking for the morning. I'm kind of beat, still a little sick, but I hope this tool is useful. Yeah, take it easy.